Hi, today I'm going to continue my discussion about linear finite element theory. This is part 4 in my series about theory about finite elements. In part 1 and 2, I talked about a Python implementation that I created for calculating stress and strain for two-dimensional problems. And in part 3, I introduced the principle of virtual work, which turns out to be really hard to solve by itself. And in order to do it effectively, we need something called isoparametric shape functions, which I will talk about today. So let's recall from last time, this is the equation for the principle of virtual work. It's very complicated and not obvious how you would possibly work with this or solve this equation. We have this integral over various elements here, and then we sum over all the elements. And here is the quantity we need to calculate. But how would we do that? After all, the elements that we're trying to calculate the integral over may have an odd shape like this: node 1, node 2, node 3, node 4 in a 4-noded element. It's not so easy to perform that integral. So the way you would do this and how we work through this is to introduce a transformation, a map or a transformation of coordinates from this real coordinates, where the nodes are located in the real part, into a shape function coordinates or natural coordinates for the element. In this case, we have 4 nodes still, but they are between -1 and +1, the 4 corner points here. So we can, if we can figure out how to map back and forth here, we can perform this integral in a much easier way. So we will integrate in this mapped coordinates instead of the real coordinates. And that will help us tremendously. So let's see how we can perform this mapping. And this is for plane strain quadrilateral elements that I will focus on here, and that's where my Python code was written for as well in the examples earlier. The idea here is to introduce 4 functions that I will call n1 to n4. And function 1, n1, will be, by design, should have a value 1 at the location of node 1, and then it should be 0 for the other 3 nodes. And similarly, n2 should be equal to 1 at node 2 and 0 at other nodes. n3 should be 1 for node 3, and the function n4 should be 1 at node 4. The coordinates here are given instead of x and y, we will call them xi and eta. And they will go between -1 and +1 for the 4 corners. And I claim that these equations here will do exactly that. So if you plug in and think about it a little bit, you will see that these functions actually, if you plug in these coordinates of the corners, you will get exactly these quantities that I wanted to the left there. And this is the shape functions that I want to use here. To think a little bit about numerical implementation in Python and the examples I talked about, this is how you can calculate the shape function n, which will be an array in Python. And if you know xi and eta, you can just calculate it using this equation here. So it's pretty simple. Now, back to our math equations here. We introduced these shape functions, but it wasn't really clear how we use them, perhaps. So I will talk a little bit about this next. So the shape functions n1, n2, n3, and n4 can be used if, as shown at the bottom in green. So if you know the position of the nodes in the real coordinates here. So you assume exactly where these coordinates are, which you should know, where the element is located. You can then calculate the position of any point inside that element if you know the corresponding xi and eta value using these shape functions as shown here. You just calculate n1 for that xi and eta at x1, x2, x3, and x4, like is shown here. And similarly for the y coordinates. So you can directly calculate the x and y coordinates for any point in the natural coordinate system, where that would be over here. So that's useful. That is a part of the mapping that we need to do. Let's talk about displacements. You can use the same approach for displacements. It's kind of interesting. So let's assume that we know the displacements of all the 4 nodes in the real coordinate system. So we know how these nodes are displaced. And we know the xi and eta position we're interested in. Therefore, we know the shape functions. We can calculate the displacement of that point in that element. using the shape functions. So this is exactly what one can use to calculate displacements from the nodal positions using these shape functions. To do this on the computer, we will use a vector notation and matrix notation. So I will introduce a variable called u, which is a 8x1 matrix. And I just dump in all of these nodal displacements here. And then I define a H matrix in a kind of weird way, but I'll make it a 2x8 matrix that has this shape. By defining it this way, I can calculate the nodal displacement. I can calculate the displacement of any point that's specified by natural coordinates psi and eta using this H and U. So capital U is the nodal position, H is this matrix that depends on psi and eta, and lowercase u is then the displacement of that point that is determined by psi and eta. So that's how you can calculate displacements from this mapping using shape functions. And that's really what I want to focus on here. Next time I will continue this and talk about how you can calculate strains from the nodal displacement. And then also how we can start integrating these integral equations that we started with. So once we have put all of these together, we will be in good position to start solving them. But that's all I have for now. If you have any questions, you can ask them below.